Buffers are chemical systems that resist changes in pH. Biologically, these are very important because biological functions have a very narrow pH range in which they're effective. So the pH has to be kept within that narrow range. And so we need to look and see how buffers work to keep pH within a narrow range.
When we look at buffer systems, they are usually systems that are an equilibrium that has a weak acid and the conjugate base in it. This is an equilibrium. This equilibrium resists a change in pH because you have a large amount of the weak acid and a large amount of its conjugate base in there, and so adding base reacts with the weak acid, adding acid reacts with the conjugate base, but what we find is the concentration of protons stays about the same because the equilibrium adjusts. Let's look at this a little bit more closely so you can better understand. Here is a buffer system. A buffer system is composed of large quantities of a weak acid and its conjugate base. If I add a little bit of acid to this system, I increase my hydronium ion concentration. That hydronium ion concentration reacts with the conjugate base. When it reacts to the conjugate base, it shifts the equilibrium to the left, making more of the weak acid. The excess acid is consumed by the large conjugate base concentration, and it makes a little bit more weak acid, but the overall pH does not change much. That same buffer system will accommodate bases with little change in pH. If I add base, it's going to remove proton concentration from the system and reduce my hydronium ion concentration. That smaller amount of hydronium ion concentration is then replaced by the large quantity of weak acid because it dissociates and makes a little bit more of the hydronium ion. pH doesn't change much then. buffers in the blood can be overloaded, however. Let's look at respiratory acidosis. There's something called respiratory acidosis, which comes when you're not blowing out enough carbon dioxide. When you're not blowing out enough carbon dioxide, then what happens is the carbon dioxide levels start building up in your blood. When carbon dioxide levels start building up in your blood, well, then your proton concentration increases. That drives this reaction to the right, increasing your proton concentration, and your pH will become too low. You can have something called respiratory alkalosis by breathing too hard and blowing out too much carbon dioxide. If you blow out too much carbon dioxide, then what happens is you shift equilibrium to the left. The amount of protons being produced by carbonic acid is being pulled down, and so then your pH becomes too high. The last thing that I want to do in this chapter is go back to an acid and a base and compare the two of them when we have the same concentrations in water. Sometimes people are really confused by these concentrations, and by going through these two concentrations side by side, this often clarifies the misunderstandings that people have. We can have the same concentrations of an acid and a base, but because they're making very different things in solution, you have different concentrations of each thing. If I look at hydrochloric acid, 0.030 molar hydrochloric acid will give me a proton concentration of 0.030. If I look at 0.030 molar of sodium hydroxide, I'll see I have a concentration of hydroxide that is 0.030. Let's put these side by side in a table and look at these. These are the concentrations of the ions that I have for each of these solutions. So now what I'm going to do is put these into the table one by one, and we're going to look and see how the concentrations and the pH of these two solutions are different. Hydroxide has a concentration of sodium hydroxide has a concentration of 0.030 molar of hydroxide. Hydrochloric acid has a concentration of 0.030 molar of protons. This means that I can determine the concentration of the other ion by using this equation. I can rearrange this, but I rearrange it differently depending on what I need. Since I have hydroxide concentration with sodium hydroxide, I'm going to rearrange it in this manner so that proton concentration is 1 times 10 to the minus 14 over hydroxide. With the hydrochloric, I'm going to rearrange it in this manner so that hydroxide concentration is equal to 1 times 10 to the minus 14 divided by proton concentration. So now what I need to do is plug in my hydroxide and plug in my protons, and I can determine my other concentrations. So for my sodium hydroxide solution, I plug in my hydroxide concentration into the formula. Proton concentration is 1 times 10 to the minus 14 divided by 0.030. That gives me proton concentration is 3.3 times 10 to the minus 13. For my acid solution, I can plug into my formula hydroxide equals 1 times 10 to the minus 14 divided by proton concentration, plug in my 0.030 into the proton concentration, and I get that hydroxide concentration is 3.3 times 10 to the minus 13. Now I need to figure out my pH. For my base solution, my sodium hydroxide solution, I get my proton concentration, which is 3.3 times 10 to the minus 13. When I take my negative log of 3.3 times 10 to the minus 13, I get 12.5. For my acid solution, my proton concentration is 0.03. If I take the negative log of 0.0, I get 1.5. And so now you can see they were the same concentrations, but because the two chemicals, sodium hydroxide and hydrochloric acid, have very different concentrations of ions, the concentrations of protons, hydroxide, and pH are very different. And I hope this clarified your understanding of the pH and solution concentrations. Now remember that you need to do problems. As you read, do the in-text problems and do the end-of-chapter problems. There are a lot of group problems in this chapter, so remember to mix it up as you do the problems. Don't do one the same as the other right after each other, because that'll encourage you to memorize a way of doing problems instead of understanding the principles. There are plenty of worksheet problems for you to do, and then I will have an online quiz posted for you.